All right, so we're going to get started on this recording. Um, I think the audio from the original recording did not get recorded, unfortunately, so I will be recording this session here. So, this is, for those of you who don't know, the electronics portion of our first meeting, um, where I want to just give a basics of electronics. Hopefully, you guys get a comprehensive or, well, beginner's understanding for electronics, and as we go on, we can learn a bit more. So, first things first, electronics is the study of electron flow and behavior. So, when we study electronics, there are two things that we are basically concerned about, and these two things are voltage and current. So, voltage is defined as the difference in electrical energy between 2 points, the difference between potential energy, in fact. It is measured in volts. Um, like a 9-volt battery, for example, would have a potential difference at the two nodes, at the positive and the negative side, and that difference would be exactly 9 volts. The potential difference is the pressure created that creates electron flow, which is current. Current is the flow of electrons through wires. Current is measured in amps. Oh, sorry about that sound. I live in Midtown and a lot of cars go by, so hopefully that's not a problem later on or anything. But yeah, current is measured in amps, often really small, so often milliamps or microamps. Um, yeah, so like you see here, we have this is a picture of a what a voltage source would look like inside a schematic. So a schematic is basically a um, blueprint of a circuit that we would like to build. So whenever you see these two parallel lines, one longer than the other, that is a voltage source. And on one side of the voltage source, it's the longer one. That's where the higher potential lies. So if this was 9 volts, then this part would be 9 volts, and then this part would be that difference, so 0 volts. So zero as it goes along, it increases to 9, and then everything up here is 9 volts. So this is a current source. It is a circle with an arrow through it, and then yeah. So current, that means that current along this branch, this wire here, would be flowing at a rate of whatever this current source is set to. Sometimes you'll also see voltage sources as a circle with a plus and a minus. That's just another way to draw a voltage source. So a lot of people like the analogy of electricity as a water hose. I think it's a pretty good one. Voltage would be the pressure that is forcing water to be flown through a hose, or in this case, the case of electricity, it'd be a wire. A current is kind of the size of the hose. The size of the hose determines how much um, how much water can flow through at any given time. And then resistance, as we'll talk about in 1 second, is the sand or some kind of sediment or something like that inside the hose that's impeding the flow. So resistance slows down the flow of electrons, or I guess in this case it'd be water. So resistance is the relation between voltage drop and current. So you can see this green is kind of fading out as it goes along this zigzag. This zigzag is a resistor. Specifically, it's a 1K resistor. So you can see this green is fading. So in this little simulation that I'm going to show you guys more of in a second, this is called, or this is the green. The brighter the green is, the higher the voltage is at that point. So as it crosses the resistor, the voltage drops. So how much does it drop exactly? Well, you can calculate that by this handy formula. This is called Ohm's law. So Ohm's law is the current equals voltage divided by resistance. So if we have a voltage on this side and a voltage on this side, the V here is the voltage drop. So the point here, the voltage here minus the voltage here divided by this resistance, 1, which is 1,000. And then from that, we can calculate the current, and we can calculate how fast electrons are moving in this whole circle, or in this whole circuit. So voltage is consumed. You can think of it like voltage is consumed because the voltage is dropping across this resistor. So we can do a pretty simple circuit analysis here. V is 5 volts. By V, I mean the voltage of this source. And we have R is 1,000, so that's this resistor over here. So this is an example of a schematic, a little circuit that basically shows us what's going on. Oops, excuse me. So we can calculate very easily from Ohm's law that the current going through all of this is this V divided by this R. So that would give us 5 milliamps. One thing to point out is that, right, so like the water analogy, since this is a closed loop, there's only, so the flow of water through this entire loop is going to be the same thing. So we're going to see a little bit more complex cases a little bit further on. So capacitors and inductors. Capacitors and inductors are two different components that people might use. Obviously, there's hundreds more that we're not going to talk about at all. So capacitors and inductors have relations between the voltage drop across them and the current going through them. Typically, when we talk about voltage, we say voltage across, and then when we say current, we say current through. So just, keep that in mind, I guess. I don't think people are too much of sticklers for it, so it's okay. But so they do have equations that define the voltage across them and the current through them, but they're not linear like this, where the relation is just a multiplication by R. They have more complex ones a little bit, where the capacitor both of them are either derivatives or what are they called? Integrals. Integrals. That's the opposite of derivative. Integrals of each other. And we aren't going to do any of that calculations because it's just gross. So for now, we can think of them as magic boxes. These pictures right here, these are what they would look like in a circuit. So this two parallel plates, you might have heard the term parallel plate capacitor. That's where this comes from, because inside here is two plates with a inductor, not inductor, sorry, insulator in between, um, and then it does magic stuff. And then the inductor is a wire that's wrapped around some type of metal, and this does something that we don't have to worry about. So its symbol kind of looks like if you wrapped a wire around a imaginary bar right here. Magic boxes. So a little bit stepping into more complex circuit analysis. We have two laws by this guy named Kirchhoff. The first of which is the current law, and that states that the sum of currents into a node is the sum of currents out of a node. So let's think of this as a water analogy, right? Let's say that this is some central hub, and then all of these are pipes coming into / out of that central hub. The amount of water that comes in has to go somewhere, right? I1 is one of the sources coming in. I3 is another, and I5 is the last one. So all of that water has to go somewhere. So because, well, this has only a limited amount of space, right? So that means that everything that comes in has to go out at whatever other nodes. So namely I2 and I4. And we can write this as I1 plus I3 plus I5 equals I2 plus I4. Here's a more circuity example. Circuity. circuity example where you have this I total coming down this path, and then you can think of some of the waters being dropped into IR1, and then the rest keeps going. And then some of that water gets dropped into IR2, and the rest keeps going. And then the rest of that water gets dropped into IR3. And then back when it connects to here, it'll connect back with IR2, and then it'll come back and connect with IR1, and then bam, there's your I total again. So these they're called nodes, points where things connect, but this whole thing is also called a node. Now, why is that? They're called a node because they share a voltage. When something has just a wire between it, there's no voltage drop across the wire. There's no resistance across the wire. So that means that there cannot be any voltage drop across the wire if we think about I equals V divided by R. So that means that all of these share a voltage. When that happens, we call that a node. 3 and 6 are not common nodes because there's a voltage drop between them. Hopefully that helps you guys understand what I mean by nodes going forward. Right, we'll see some more examples of that. So the other Kirchhoff law is Kirchhoff's voltage law, and that states that the sum of all voltage drops in a loop is 0. So the voltage drop between A and B plus the voltage drop between B and C plus the voltage drop between C and D plus the voltage drop between D and A. And you might be thinking to yourself, wait a minute, what about this one? So there's a voltage drop right here. Now what about coming back? So you can think of this voltage source as a negative voltage drop, right? If it's applying voltage, like injecting voltage into the circuit, then it's quote unquote dropping it by a negative amount or increasing the voltage. So the voltage gained here has to be lost here to make it back to itself. And that's Kirchhoff's voltage law. So it turns out that these two equations, you can use these to solve basically any circuit. Very uglily, because you'll be creating basically massive systems of equations, systems of linear equations that are not fun to solve. So, yeah. So there's some tricks that can help us to simplify things. And one of those is series and parallel. So series and parallel are ways to connect components, namely resistors, to simplify the circuit for easier analysis. So right here we have an example of a series circuit. We have this resistor, let's call that R1. We have this resistor, let's call that R2. And then we have this resistor, let's call that R3. Now, it would be really nice if instead of 3 resistors, we would have 1 resistor. Right, so if we could group them all together, it'd be much easier to solve the current going in. Whatever voltage drops coming out and all that stuff. So it turns out that because these are placed in series, and by that I mean I go across this resistor, and then I only go across this resistor, and then I only go across this resistor. It turns out that we can replace all of these with just one resistor with value R1 plus R2 plus R3. You can derive this by seeing that the current through all of these has to be the same. Now, parallel is similar, but swap out the current with voltage. Now you have this node here, right? So this node connects all of these 3 points. And then you have this node here, which is all of these 3 points. Now, because the voltage in a node is the same, right? The voltage all here is the same as itself, and the voltage all here is the same as itself. Now, the drop between each of these resistors has to be that amount, right? The drop between this point and this point is the same as the drop from this point to this point, because these are connected and these are connected. So these are called in parallel, and we have a formula to calculate the equivalent resistance of all of this. So if we wanted to replace this with just one resistor, and that is this formula here. It looks a lot like this one, but all of the terms have a 1 divided by in front of them. So 1 divided by R is equal to 1 divided by R1. You can't see that, but that's R1. Plus 1 divided by R2 plus 1 divided by R3. And a useful formula that you guys would probably like to know is that the total resistance of two resistors in parallel is you multiply it and then you divide it by their sum. You multiply it and then divide it by their sum. It's not too hard to calculate. A lot better than, nested fractions and such. Yeah. And so let's try an example here. So we have the circuit here. We have a voltage source that's putting 5 volts into the system. We have this resistor coming down, 3K. We have this 1K, and then we have this 1K. And we have this thing here. This is called a ground. So this basically takes any point in a circuit and hard drives it to 0. So this has to satisfy. This is like the first thing that has to satisfy that this point and all of the wires connecting to it are 0 volts, right? So, yeah, we can talk more about that in a second. But so first thing we see here is that we have these 3 resistors, and we'd really like to find the equivalent resistance of this network. So are any of these in parallel? Well, it doesn't look like it because this resistor, this 1K resistor up here, connects this node with this node. This 3K resistor connects this node with this node. And this 1K resistor connects this node with this node. So it doesn't look like any of them are sharing the same 2 nodes. None of them are crossing the same 2 nodes. So none of them are in parallel. But we do have this 1K resistor and this 1K resistor in series. How can we see that? We have one node going into this resistor and out to this node. And then from that node, you only go down this resistor and down to this last node. So series resistance, we can add them together, right? We can use that formula. So now we have this 3K resistor and this 2K resistor. Now is anything in parallel? Well, we see that the 3K resistor crosses between this node here and this node here. And this 2K resistor crosses between this node here and this node here. And you can see that they are in parallel because all of these 3 points up here are the same voltage, right? Because all that's between them is a wire. And the same goes for these 3 points down here. So that means that these two are in parallel. We can use that formula that we found above where you multiply them and then divide by their sum to come to a final resistance, a final equivalent resistance of 1.2K. So now it's as simple as the first problem that we saw. We can just divide the V divided by 1.2K, and that'll give us an answer for I. So that should be, I believe, 4.183. I had this written down. I should know it. But one thing we can do is instead of all that, we can go check it. So this is called Falstad Circuit Simulator. This looks daunting at first, but let's start easy. So Falstad is a circuit simulator that lets you model any schematic, any circuit here, and then it'll show you what's going on, the voltages at points, the currents across points, or currents across components, all as a function of time. You can do some pretty neat stuff with this. For now, let's start with a simple circuit, the one that we had above. So let's start with that voltage source, and they usually default to 5 volts, which is what the problem asked for. Right then I just hit W for wire. That's just a hotkey. You can do the same thing with resistors. We had one here, I believe, one here, and then one here. And then we had a wire here and a wire here. Last thing is we had a ground right here. So that sets the voltage here to 0. We can also see what happens if we put that there. So now this sets this to 0, and now you can see that the voltage at this node is -5 because this has to be 5 less than this because of this voltage source. So we can move it from here and see that this is 5 because this node has to be 5 greater than this one, right? Yeah, and moving it anywhere along this node is the same thing, right? Because they're the same node. So we had 1K here, 1K here, and then I think we had a 3K right there. So, wait, let's check that. Yeah, okay. That's the circuit that we had. And we want to find the current at this point. So what we can do is just hover over it, and then it should give you... Okay, I was off by a little bit. It is 4.167. But yeah, you can check on your calculators that that is indeed 5 divided by 1.2. Yeah, so that's Falstad. It's pretty neat. We can talk more about it in a bit once we get to, like, yeah, we could talk more about it in a second. For now, so this is a breadboard. No relation to bread, other than it kind of looks like it. I think that is actually why it's called a breadboard because all these holes look like the holes in bread. Um, Maybe fact check me on that and get back to me. But so this is used to prototype circuits. You can see this here is a pretty basic circuit. You have one resistor and one LED. So this is probably all it does is light up an LED. So what's going on here? What are all these holes doing? Well, all of these holes are offering connections. So each of these little holes is a um, is a header for a pin. So you can stick, like, see what they did here. They stuck a resistor into one of these holes. And then underneath all this plastic, all this white plastic, there is a metal connection going on that connects every row. So this one, this one, this one, this one, and this one are all connected by metal. Like each one of these pins, I think, has like a little clamp in it, like a little spring clamp. So when you put a pin into it, like a resistor or one of these pins, we'll talk about that in a sec, or like an LED pin into it, it'll grab onto it and then it'll conduct electricity through it. So when it does that, it'll connect it with all of the other pins in its column, I guess. Depends on how you look at it. Maybe this is row. I don't know. So this is useful because now we can build circuits on this. We can put connections here. So let's look at this one. We got the resistor coming down, connects here, and now see how they connect vertically. This one now connects to the LED, which connects to your ground. These are called power rails on the side, and they connect horizontally, the long way. Yeah, let's say that, the long way and the short way. Power rails connect the long way on both sides. Sometimes you'll see them as a plus and a minus on each side. Sometimes you'll see it as a plus on one side and a minus on the other side. Usually this minus is referring to ground. So you start at the positive voltage, the high voltage, and then it'll fall down the resistor and fall down the LED to ground. And then you can attach a voltage source at the ground and at the positive to complete that circuit and then power the LED. This is something that we did on Monday, the 19th. We were using Arduinos instead of power. So, yeah, there's this rivet in the middle of the breadboard, and that's called the ravine. So there's no connections between the ravine, and that's for a reason. That's because these little things, these are called ICs. We'll talk about that in 1 second. These are called ICs, have somewhere to sit so that their pins don't cross each other and then mess up connections in between them. Right. So ICs, what are they? They stand for integrated circuits. They're basically little chips with thousands or millions of tiny, tiny little resistors, capacitors, inductors, op amps, transistors, you know, all that jazz inside of it. So, what purpose do they serve? They can basically do anything you want. Um, they're basically, you can kind of think of them as methods in coding. They simplify your circuit, they have a bunch of inputs, and then they have a few outputs. And instead of having to build it every time, you can just plop an IC into your circuit, and then that should do the trick for you. So this is an example of what you'll find in what's called a data sheet. A data sheet is a online document for every IC that will tell you like how it works, operating temperatures, operating range, stuff like that. We'll talk about that more later on when we get to circuit design and stuff like that. But you can see that it labels all the inputs. You got the inverting input, non-inverting input, the powers, inputs, and then an output. So this is a functional block diagram inside. Functional block diagrams help simplify. So you're not looking at a bunch of transistors and resistors and capacitors. Instead of you're looking at something familiar. In this case, this triangle is called an op amp. Um, yeah. So op amps, sorry, no. ICs come in two general classes. One of them is called DIPs, dual inline packaging, dual inline packages, actually, I think. And those are the ones that you've seen on the last slide where they have two lines. Okay, no, two lines of pins like this, right? Two lines of pins like this, dual inline and packaging, and those are used on breadboards. So these are examples. Um, this one here is an example, and the good thing about these is that they're very easy to use. They're very easy to just stick in a breadboard, just power it up, and then you can use it right there. So the other one is called surface mount, and surface mount is has to go through a process called soldering. Soldering, we did that also. Actually, we did that last Friday, where we got to play around with solders and try soldering something. So these are surface mount onto what's called a PCB. So they come in lots of shapes and sizes. Generally, they are, um, well, okay, I don't want to say they're more high performance, but they're used more in high performance equipment just because of their size, right? Because breadboards, inline packaging, you need this big thing. Soldering, you can see how tiny these little pins are. So much easier, so much smaller, so much more practical in the real world. But these are great for prototyping, don't get me wrong. We will be using them hopefully sometime soon. If not, we will be using um, boards that have them on it. So, right, I mentioned that uh, surface mount ICs are soldered onto a PCB. So, what is a PCB? PCB is a printed circuit board, and these are software design boards using a CAD software like AutoCAD. Sorry, not AutoCAD. Um, a CAD software like Altium, Eagle. In this club, we're going to use KiCad, or I think someone said it's called KiCad. It's KICAD. Pronounce it however you want. And we're going to use that to look at a PCB and see how it's designed. So Um, these little holes here, these little black holes here are through holes that you can put a something like a dual inline package IC into it and then solder that on. I keep bringing up this solder. I promise I'll talk about it in a second. Solder that on, and there's also these little just white pads with no holes inside of it. So these are the what's called footprints. Footprints is basically where a component is going to go. These are footprints for the ICs that are surface mount. So we would solder those onto these footprints, and then that would help, or that would give us a more permanent solution to to our breadboard alternatives. These are generally smaller because we don't need all of those holes. Instead, we have what's called traces. So all of these lines are called traces. And what they do is basically act as wires in a circuit to connect pins. So, I mean, this is like a stock photo, but like something like this, I can't zoom. Something like this, you see this trace is connecting this pin to, looks like this pin to me, but maybe I'm wrong. But you get the point. These traces are very, very tiny wires under the silk, like the silk screen that lets electricity conduct between points on a PCB. So generally PCBs are multi-layered. This one looks pretty standard size to me, but so if you flip it over, sometimes PCBs are going to look totally different. That's because they are multi-layered. You can solder on both sides, although I wouldn't recommend it in in a lot of cases because it's difficult. But you can do it. Sometimes they're up to like 32 layers thick. I think 32 layers of all of this stuff with only footprints on the outsides. So they travel between the layers called the with things called vias, these little holes, these little tiny circles that let um, that that traces travel down through the PCB. Okay, solder. We talked about. I've mentioned this a few times, and so what is soldering? Soldering is basically using a very hot lead, this thing, to melt a bit of solder filler. I call it solder filler. Other people call it just solder. I like calling it solder filler. To basically bind two pieces of metal together. So it's kind of like welding on a super, super, super small scale, like a tenth of an inch scale. I guess you can think of it like that. But what it does is it melts them together, binds them together, and the metal acts as a conductor. So when you bind it together, like an IC onto a PCB, then they will conduct electricity with each other, which is super useful in electronics. The lead will get very hot. Leads often get up to 700-800 degrees. I think the ones in our labs get up to like 700 degrees. So please don't touch it with your hand. Please like tie your hair back. Don't wear sleeves. Like not okay. Don't don't wear like baggy sleeves because it is dangerous. Um, these solder filler often takes about 300 degrees to melt, which is more than enough to burn you, um, more than enough to hurt you. So yeah, solder paste is an option for very, very precise work, which is where you have the solder paste made out of tin and lead. Don't worry, the lead is safe. The solder is also completely oops. The solder is also completely safe nowadays. I believe back in the day it wasn't as safe. Like it had toxic lead in it, so you'll be fine now. Okay, all right, this isn't dangerous at all. But they do still use lead, safe lead, in solder paste, where you squirt a little bit of the paste onto the footprint, and then you put the IC right over the paste that you just put, and then you put all of this, PCB included, into a kiln, and the kiln will melt the paste, the iron and the lead and the tin in the paste, and then make that bind. So it's just another way of solder. Um, it's it's better for more accurate things. But for these pins, you could tell he's soldering pins. Um, Lead works just fine. So I'm going to show you a tiny little demo here, just a few minutes of this, just to get yourself familiar with soldering.
When it cools and solidifies, it fuses to the surface of a metal at the molecular level, providing good electrical conductivity between two metal surfaces. Solder normally contains flux, which helps the solder to flow, and also helps make a good contact by removing the oxides on the surface of the metals being joined. Although modern flux is not toxic, when soldering you should always use a fume extractor to prevent the fumes from the flux irritating your lungs. The fumes are extracted by a high-efficiency particulate air filter, or HEPA filter, before the air is returned to the room. Before you handle the components, it's strongly advised that you wear an earthing band to prevent electrostatic damage to the components. There are two different soldering types, surface mount and through-hole. Surface mount connections are made by heating components with pre-applied solder in an oven so that it melts and joins to the surface of the board. For this tutorial, we'll look at plated through-hole soldering, which is done on boards with printed circuits on both sides. Through-hole soldering is when components are pushed through a hole in the board and soldered from the other side. The solder flows through the hole to make the best possible contact. First, take your component and create a bend in the legs with a pair of pliers, so that each leg is at a right angle. Push the legs through the holes in the board at the appropriate place and push it all the way down. Then turn the board over and bend the legs slightly to lock the component in place. When the iron is up to temperature, first clean the tip of the iron on the wet sponge on the iron holder to remove any excess solder and flux residue that might be there. You then apply heat directly to the pad for about a second, before placing the solder in contact with the pad. When the solder starts to melt, feed it in for about a second. Take the solder away, but leave the iron on the pad for another second. Then take the iron away and let the connection cool. Let's have another look at that. Before you make another connection, it's important to remove any excess solder remaining on the tip of the iron. This is because any flux in the solder will vaporize until there's none remaining. If you try to make a connection with solder without any flux in it, you risk making a bad connection. When you turn the board over, you should see that the solder has flowed through the hole by capillary action.
So yeah, that's soldering. You can see this very, very clean connection here. Looks very nice, conducts very nice, and yeah, that's why we use it.
When it cools and solidifies.
Okay, we're switching directions here a little bit, and we're going to talk a little bit about microcontroller units. So this is a Arduino Uno. Arduino is a company that makes microcontrollers. Um, Microcontrollers are basically very, very powerful printed circuit boards that can do a lot of different functions. So Arduino's an example, and this one down here, this is called a Teensy. Teensy is basically a very, very powerful version of a Arduino. It's faster, it has more storage, has more pins. Uh, yeah, maybe it has a little less functionality, but still very good. You know. In this club, we bought a few Teensies, but we will be using some Arduinos every now and then to get familiar with the code. And yeah, so yes, so this is called a pinout diagram. And this is important because it shows you what each of the pins on the on the microcontroller can do. In this case, this is a Teensy. Arduino has like a signature blue color that you'll be able to recognize. This is a teensy. They're all green, but don't assume it's a teensy just because it's a green. So yeah, so this is called a pinout diagram. Um, it tells you what each of the pins do. Along these, yeah, so along this, um, on the board, it'll tell you what number the pin is for some of these. 0, 1, 2, 3, and yada yada yada. So these gray blocks on the side tell you that those pins are digital pins. And what digital pin means that is that it can output a 0 or a 1. 1 being yes, there is voltage there, and 0 being no, there's not voltage there. And it'll be able to tell. So these orange ones are called analog pins. It looks like there's 10, 11. There's probably, I think there's one on the underside of this. 12, maybe more, 13, I don't know. So analog pins are pins that don't send digital info, they send a um, a continuum of info, right? You can like you can simulate like a sinusoid, um, ramp wave, any info that would need more data than just a 1 or a 0, right? PWM pins are called pulse width modulation pins. We are going to be using these to hopefully drive the motors of the robot. More details on these to come. Touch sense pins, I don't know. I've never used those. Don't worry about those. Serial ports are for connecting for information. Think your USB. Your USB is a serial port. This thing is also communicating through serial. We also have I2C and SPI, and both of those are basically just ways to communicate with other boards, with and clocks and other data that they would need to sync themselves. Right. So this is what Arduino IDE looks like. If you haven't downloaded Arduino, please do so. Um, it'd be very useful in the future. We're not going to go through any of the code today because we're kind of running out of time. But yeah, definitely in another lecture. And there is one more thing I wanted to talk about, which is I'm going to show you guys in Falstad. So we talked about the voltage sources, which is these, right? There's also a different type of voltage source called AC voltage source. So this gives us something like this. And the reason, okay, so this type of voltage source is called DC. It might be a little bit confusing because maybe it should be called constant current or constant voltage. DC, of course, being standing for direct current, and AC stands for alternating current, which I guess is a pretty good name for it. But what happens is that in an AC, the voltage being outputted, even if they're both connected to ground here, you can see that it's alternating, right? Remember that green in this is a positive voltage and red is a negative voltage. So let's see what's going on here. Let's put a, oh yeah, Falstad has this great thing called scopes. Scope meaning oscilloscope, which is what electrical engineers use to measure voltages and currents and all that stuff as a function of time. So look at this. This is a oscilloscope capture of this alternating current. You can see that it makes like a sine wave, right? And that's because we set this to sine wave. So double click that, and then the classic is an AC sine wave. But there's also square wave, and look at that, that changed the picture. So let's reset that and see what that looks like. Square wave, nice. 1, negative 1, 1, negative 1, 1, negative 1. That's cool. So let's stop that. And there's a few other ones. There's triangle. These are more rare, but square and sine AC are definitely very, very useful, especially in other applications that we're not going to talk too much about here. But one thing that they can do is encode information, right? They can encode information in terms of the amplitude and the frequency and the phase of a wave, and that's very helpful in signal processing, and yeah, other stuff like that. So, right, another reason why AC is used, I'm sure you might be wondering why AC is used, is the efficiency. AC ends up being a lot more efficient when you're talking about like large scale power applications. That's why our transmission lines, those big tower things, they're carrying AC, and then once they get to your home, they get converted to DC. So they can do that in a fraction of the energy loss that DC would. Um, but yeah, so I think for Oh, right. So they also act at frequencies. So let's see what happens. I'm going to change this back to AC and then reset this. So let's see what happens when I change the frequency. Let's make it 400. Nice. The frequency increased, and that means that the speed at which it oscillates um, between high and low is increasing, and we can use that to do some pretty cool stuff. Um, ACs have pretty weird relations with things like capacitors and inductors that might be beyond the scope of this. But if you want to know, definitely come ask me about it because I'd love to talk about it. But yeah, what else is there? Outputs and labels. You can measure the voltage at any point relative to another point. So let's see here. Reset. Nice. And that's outputting it. Ohm meters. Ohm being um, the units of a resistor. So you can build any resistor net if you want here. Let's do something crazy like this. And you can measure the resistance, the equivalent resistance if you were from this point to this point. Super cool tool. Um, yeah, play around with that. That's pretty cool. What else is there? Um, Capacitors, bam. Inductors, bam, right there. Switches, pretty cool. You can click it and it switches to build some pretty nice circuits. But yeah, I think that's a good basics on Falstad. Um, Play around with it if you want. Oh, yeah, current source right here. Current sources, you don't see them a lot in schematics. They're what you call unideal, meaning that they can't actually be created like as real things in the real world because physics. You can build things to simulate them, but it ends up being that voltage sources, either DC or AC, are a lot more accurate, have less like negative impacts on like stuff like loading, um, and yeah. So I hope you enjoyed this brief lecture on robotics, uh, intro to robotics. And if you have any questions at any time, please reach out to either me or Richie. Um, and yeah, thanks for listening.